Okay, this is our Hansho edition of the Transformations lecture. For those of you at Hansho, I hope you're watching. Um, we are doing section D, which is stretches. On page 143, if you're doing the reading, you should recall our transformation investigation where we worked with this complicated looking function, which is actually an M-shaped function. So I'm just asking a few questions here about what you remember, and maybe you don't remember. So I'm going to show you here exactly what happened. So what happened when P grew bigger? And I'm just going to show you that. And when P grew bigger, it stretched vertically, right? What about when Q grew bigger? Oh, when Q grew bigger, it compressed horizontally. I don't think compressed is the right word. There's probably a better word, but okay. And then what's weird with the Q is it's like when it gets to zero, it maximizes, and then when it starts getting negative again, it shrinks again. So when Q gets big positive, it compresses, and when it gets big negative, it also compressed. So when is it maximum? So when it's zero, when Q goes to zero, then it is normal size or whatever. It's the biggest size that it can be. Okay? All right. Let's move on to our problems. Okay, so first, sketch on the same set of axes the graphs of y equals f of x, y equals 2f of x, and y equals 3f of x for each. So we'll start and we'll do A, C, and E for this one. Okay, and since I always do the parabola, you're probably sick of that. So I will do, and I also always do the hyperbola. So how about if I do e to the x? Okay, so which would e to the x look like? Well, first we draw a normal e to the x. We draw our axes. And if you remember e to the x, like all exponential curves, as long as there's no multiplier in front, it crosses at 0, comma 1. And then at the value x equals 1, e to the x becomes e to the 1, which is like 2.71. Okay? And then we draw the curve. Looks kind of like that. Now, what does it look like if we do, and so like if we draw the points we just used there, we used 0, 1, and we used 1 and 2.71, which is the value for E. Okay, now what if we did y equals 2f of x, what happens? So in this case, if we did 0 and 1, instead of getting 0 and 1 out, we'll get 2 out, right? Because the 1 would be multiplied by 2. And then when we put 1 in, instead of getting e out, we'll get 2 times e, which is going to be about 5.42. Okay? And so if we were going to graph that, this point would be at 2, this point would be at 5.42. It would look kind of like that. Okay? And then if we did y equals 3f of x, which is this one, and we'll use a different color, like brown, it'll be even more steep. So instead of going through 2 here, it'll go through 3. Okay, instead of going through 5.4, it'll be more like 8 or something like that. Okay, so like each time it's just getting steeper and steeper or higher. All right, so you can do the other two graphs there. 2. Sketch on the same set of axes the graphs of y equals f of x, y equals half f of x, and y equals a quarter f of x. And it says to do these two, but you can choose x cubed if you're bored of doing parabolas and exponentials. Let's see, we'll do x squared this time. Remember, it goes through 0, 0, negative 1, 1, negative 2, 4. Okay, looks kind of like this. Okay, and then what if we were going to do half of f of x? What does it look like? Well, actually, half of f of x is going to make it like instead of going through 0, 0, it's going to be going, well, 0, 0 is the same. Instead of going through 1, comma 1, it'll go through 1, comma a half. Instead of going 2, comma 4, it's going to go through 2, comma 2. Okay, so it's just going to be flatter. Okay, and then what if it's a quarter x? Well, if it's a quarter x, then it'll go through, like for example, if I draw a little table here. So like originally I have like negative 2, negative 1, 0, 1, 2. I'm going to have, for a regular parabola, I have 4, 1, 0, 1, 4, right? What if I'm doing 1/4 times the y's? What am I going to get? Well, everything's going to be a fourth smaller. So like for example, for negative 2, I'm going to get, instead of 4, I'm going to get 1, right? The 0 value is still 0. And for instead of negative 1, or instead of 1, I'm going to get 1/4. Okay, so it's going to be an extremely flat parabola where 2 is negative 2 and 2, comma 1. Okay, so it'll just be flatter. All right? Okay. I'll let you do the other one on by yourself. Sketch on the same set of axes the graph of y equals f of x and y equals f with 2x inside. Now, what does that look like? Now, this is kind of different. So, for example, let's take the C one, since, let's see, if we have x plus 3 here, and we're going to do a translation. Actually, first let's just graph the function so that you can see what it looks like. If you have y equals x plus 3 squared, that is basically if it's x minus a, which is the standard form, a is negative 3, so that means you're moving it 3 to the left. It's kind of counterintuitive, but hopefully you're getting used to it now. The x minus a one. Okay, so that's what x plus 3 quantity squared looks like. What does it look like if you do f of 2x? Okay, well, if you do f of 2x, then you're going to put 2x in for the x. Remember when we did composite functions? Okay, and then we have 2x plus 3 squared. And so what's going to happen here? Well, let's make a little table and find out. If we put in 0, we get 9. Okay, so we're kind of like at the edge of a, or we're at the side of a parabola now. Let's see, if we put in like negative 1.5, and the reason why I chose that is if I put negative 1.5 in there, it'll be negative 3 plus 3, 0. So that is probably going to be the vertex. And then if negative 1.5 is the vertex and 0 is all the way up at 9, probably if I put like negative 3, I'm also going to get 9. So if I put negative 3 in here, I get negative 6 plus 3, negative 3 squared, 9, yeah. So basically, this new version of the parabola is going to, let's see, it's going to be centered at negative 1.5 comma 0. It's going to be right there. And it is going to be much steeper because at 0 it is already at 9, and at negative 3 it is also at 9, so it's a much steeper parabola. So putting 2x inside the f of the function f is going to compress it, and that should not surprise us because we already saw that when you have a q value, what happens with q? When you have a big Q, it's going to compress it, and that's exactly what we saw here. When we have 2 instead of 1, it compresses the graph. Okay. One thing that we also see though is that, like, if it's an off-center parabola, the off-centerness also compresses. Okay. Okay, moving on. Number 4, sketch on the same set of axes the graphs of y equals f of x and y equals f of x divided by 2. Okay, so this is similar to what we just did, but instead of 2x, now we have 1/2 x, okay? And if we have 1/2 x, what do you think is going to happen? Well, what we predicted, or what we said before about a smaller, getting closer to 0, it actually it compresses less, right? So it's not going to compress as much, or it's going to get bigger, right? So instead of compressing uh, horizontally, it will probably grow horizontally. So let's try to, just to vary a little bit, we'll use y equals x plus 2 squared. And so we will graph the regular parabola first. Or actually, we're going to graph the off-center parabola because this was going to be off-center by -2. It's going to be centered there. Okay, that's the parabola. And then what happens if we put x divided by 2 in for x? And then we're going to get this function. And then we're going to make our little table and see what we get. So when x is 0, we have 4. When x is 2, we have 9. So I guess we're going in the wrong direction. What if we put -2? We'll get 1. Okay, and so if we put -4, we're going to get the vertex. Okay, so the -4 is going to be the vertex. And at -2, you're going to have comma 1. And at 2, you're going to... at 2, you're going to have 9. Okay, and at 0, you're going to have 4. So you can see that this parabola is going to be kind of like, wider. Okay, so even though like it looks like it might get smaller because you multiply it by 1/2, it actually gets wider. Okay, and that agrees with our prediction here. When q gets close to 0, then it becomes wider, like normal size, but it becomes wider and not compressed. Okay, so I'll leave the other one to you. Number 5, sketch on the same set of axes the graphs of, and now they have 3 divided by x instead. And so you just need to do the same thing. You make a little table and you try a few values, particularly around x equals 0, and see what happens to the graph. And we can already have a prediction that it is going to compress, right? Because if we have this p-value inside multiplied times the x, it has a tendency to compress the graph. Okay. And so here we are at number 6. Consider the function x squared. On the same set of axes, sketch the graphs of f of x and 3 times f of x minus 2 plus 1, and y equals 2 f of x plus 1 minus 3. And so they're just giving us some variations here. And why don't we do a complicated one? We could do this one here. Okay, we'll do C. So the original graph is just x squared. Y equals x squared, which we've graphed so many times now. You can just do it just like that, right? And then now if we look at this one, it's kind of a, it's got like 3 things going here, or maybe even 4. I mean, look at all these multipliers here. We have a an a value of 5. We have a b value of 1. We have a p value of 2. Okay, or is that a q value? I don't even remember. One of them's p and one of them's q. Is p on the outside, right? Yeah, p on the outside, q on the inside. Okay, so p on the outside, q on the inside. So p is 1/4, q is 2, a is equal to -5. Be careful because it's minus a. B is equal to 1. Okay, so based on all that, we can make a prediction about what it's going to look like, right? Because a has a tendency to move it to the left by 5. B has a tendency to move it up by 1. Okay, so it's going to move to the left and then up 1. We know that Q A big Q has a tendency to compress it, so it's probably going to be kind of compressed. And a p-value is going to have a tendency of, this one is going to have a tendency of making it short. So this is going to be interesting because the p and the q might kind of work against each other. So the only way to figure it out without the calculator is to make a little table and put in some values. We can already see from our prediction about where it's going to go that probably the vertex is going to be, you know, to the left a little bit. I've skipped ahead here a little bit and I found some values here. Coincidence, 0 and -5 both have the same height, so the vertex is going to be halfway in between. We find that the vertex is at -2.5, comma 1, and so that would be about, let's see, oops, let me redraw in red the regular parabola, and now let's see, the vertex is going to be at -2.5, comma 1, and then these other points, like at 0, it's going to be at 7.25, which is quite high. At -5, it will also be at 7.25. So it's not really really different width-wise from the original parabola. Maybe a little bit wider, but you know, kind of still in proportion. But you can see that it did move to the left and a little bit to the up, a little bit up. Okay, so that's what happens with this very complicated function here, and you can do this without the calculator, but I think that probably they won't ask you to do one this complicated. Number 7, given the following points lie on y equals f of x, find the coordinates of the point each moves to under the transformation y equals 3f 2 to the x. Okay, so let's take just like this first point here and see where that goes. So if you have y equals 3 of f of 2x, let's just go back and remember what each one of these does. This is the q value. The q value, when it gets bigger, it compresses. So it's going to make the point closer to the y-axis. So instead of being, and remember it compresses in the x direction. Okay, so compresses in the x direction. So the 2 value is, or the 3 value is going to be 1.5 instead, because it's going to compress by a factor of 1/2. Okay, and then the 3 value here is going to actually make the graph taller in the y direction. So the y value is -5. It's going to be multiplied times 3, and we'll get -15. So for example, the 3 comma -5 point is going to be 1.5 comma -15, for example. Okay, and then it says find the points on f of x which are moved to the following points under the transformation. So in this case, they're going the opposite direction. So like up here, what we're going to do is we're going to say, okay, the x coordinate is going to get multiplied times 1/2. The y coordinate is going to be multiplied times 3, okay, to get the new values. For this one, we're going to do the opposite. So we have like 2 and 1. Instead of multiplying by 1/2, we're going to divide by 1/2, which is the same thing as multiplying by 2, and we're going to divide by 3, which is same thing as multiplying by 1/3. But so instead of 2 comma 1, we're going to have 4 comma 1/3, right? Okay, so you're just doing the opposite to find these values for b, because these are your new points on the new function. You're going backwards, so everything you're going to be doing is the backwards process.